All right, here we go. Prisms, starting off chapter 12. Here is your homework. All right, so chapter 11 was about area. Chapter 12, you would think, is just about volume. Well, it turns out chapter 12 is about more than just volume. Chapter 12 is about two basic concepts. The first concept is something called surface area. Surface area is, as the name would imply, the amount of area just on the surface of a three-dimensional object. So think about if you could strip off the surface of a shape, flatten it out so it turns into two dimensions, and then calculate that area. So that's why surface area is literally in area. So it's going to be in square units. Volume, so you could probably done this before in previous classes. So take a box, just take the surface of the box, lay it flat, you basically get that shape right there, and calculate the area of that shape. Now don't panic, you don't need to write down that formula right there. We'll do that at a later date. Volume, let's see, volume would be, well, how much stuff is in there, and it's in three dimensions, so volume will be in cubic units, because the amount of stuff inside of a three-dimensional object is measured in cubic units. All right. And in the basic explanation of why cubic, well, square units, if you think about a rectangle, length times width, so kilometers times kilometers would be kilometers squared. When you're doing volume, length times width times height, then kilometers times kilometers would be, or whatever unit of your choice would be in kilometers cubed or cubic units. All right, so this is chapters of good news, bad news. Well, the good news is that there's lots of shapes and formulas and terms. That's probably more bad news. But the good news is that it's just basically plug and chuck. There's lots of formulas and there are lots of terms, but it all can go in your book of truth. So it's not that big of a deal in terms of the actual calculation. And you'll see that most of these are simply identify the shape, write down the formula, plug the numbers in, and chug through the calculation. And the calculations are all pretty straightforward. All right, so here we go. Today we're only going to do one basic shape, and that's the shape of a prism. So what is a prism? Well, first, more in general terms for volume, just take a whole bunch of polygons, and it could be any polygons. So for instance, maybe I have two hexagons, and then join that with, say, 6 rectangles. If we joined all of those polygons together, but we will join them only at their edges. So not in the center, but only at their edges. We get something that's called a polyhedron. And there's a depiction of a polyhedron. So we had polygon, remember, but if we join polygons, we get to this shape. It's going to be in 3 dimensions, called a polyhedron. So the definition of a polyhedron is a 3-dimensional shape made up of polygons, and those polygons must be joined at their edges. All right, second definition, it's like the first type of polyhedron. Remember, the first type of polygon was a triangle. Now we're going to come to the first one that we were going to study. This is not in terms of how many sides, it's the easiest one. They choose to always to start off with prisms. I know when I first learned about prisms, probably in middle school, I would always think about that scientific shape called a prism where light goes through and it breaks it up into a rainbow. That is a form of a prism. The prisms we're going to talk about are just the geometric shape. And so that shape is, well, it's a polyhedron, so it'll be in 3 dimensions, but it consists of 2 congruent parts. So you will have 2 congruent parts. That prism, for instance, pick any sort of polygon and make 2 of them be congruent. So, for instance, pick hexagons, take 2 congruent hexagons, and then join those 2 hexagons with parallelograms, and you form this shape called a prism. So take 2 congruent, in this case, pentagons, join them with parallelograms, and notice we get to this shape, and that shape right there is called a prism. A box is a prism. It's made up of 2 rectangles joined with other rectangles, and since rectangles are parallelograms, a box is a prism. Box are the most common type that you see. Now, we don't call them box, we call them rectangular prisms. The shape right there on the bottom right there, this shape right here, that's a pentagonal prism. But a prism just requires you to have two congruent shapes. You can have two congruent triangles, but the sides must be parallelograms. Don't confuse prisms with pyramids. And you're like, well, how could I ever confuse that with a pyramid? Well, when you have a prism made up of two congruent triangles, occasionally I'll have students think of that as a pyramid. All right, this whole chapter is going to be about two things. It's going to be about the surface area of the shape, and it's going to be about the volume of the shape. All right, we have a lot of vocabulary words to go over. So we're going to go parts of a prism. There's a lot of definitions here. If I go too fast, pause, rewind, you know the drill. All right, so there's an example of one of, an infinite number of prisms that you can make there at the bottom, and it's got a lot of pieces, parts, and they're all labeled right there. I just want you to understand that the two bases there, why are there two large parallelograms around them? That's just showing you that those two bases are on two different planes. So the plane there, the parallelogram there, it's not part of the prism itself. It just wants you to understand that the two bases are not on the same plane, but on two parallel planes. All right, so we'll start with that. So the base are the two congruent polygons, and it's what it says what defines its shape. It's what not only defines the shape in terms of its physical shape, but also in its name. So if the bases are made of a triangle, then it's a triangular prism. If the bases are made of rectangles, then it's a rectangular prism. In this case, it's the bases are made of hexagons, so it's a hexagonal prism. Next one. If you think about the sides, the non-shaded portions right there, the sides are always going to be parallelograms. And well, we give them a fancy name. We call them the lateral face. Lateral for side, face for, I don't know, if you think about a person's face, it kind of occupies the same position there. It's not the top of the head, it's not the bottom of the head, it's their face. Next definition. If you have two faces, that lateral faces, that come together, well, the two parallelograms join together and form an edge. And that's what we call lateral edges. So the edges on the side, the lines that connect the vertices of the bases, well, those would be the sides of or the edges of the parallelograms, and they're called lateral edges. They will all be parallel to each other. So if you look at the little diagram right there where it says lateral edges, notice all those somewhat vertical lines there are all parallel to each other. There's a couple there that are dashed. Remember, we're trying to draw something in 2 dimensions. It's actually 3. So if it's in dotted line, it means you can't see it. It would be behind the object. All right, what are the vocabulary words there? The physical distance perpendicularly measured from base to base is called the altitude. Now, if you notice a little in the diagram right there, the altitude there is marked in red. It's actually not touching the two bases, but it is touching the two planes, and the two planes are parallel. Generally speaking, the altitude will either be somewhere on the edge, it'll be a lateral edge, or it'll be a dotted line going from base to base. You'll see both of those. Okay, so those are the 4 definitions. Let's do some more. So this time I don't have let's see, the previous one was a hexagonal prism. Now we have, let's see, the bases are parallel and the bases are triangles. So this would be a triangle prism. And so it turns out that if the lateral edge, you see the edge right there, if it forms a 90-degree angle with the base, or bases, I should say, then we call it a right prism. Now, there's only 2 of the angles there measured 90, but the top 2 would be 90 as well, too. And since all the lateral edges are parallel to each other, every single lateral edge that you see there on the shape forms a 90-degree angle with the base. So a right prism or prisms whose lateral faces are rectangles, and the altitude is a lateral edge. So if they were to mark the perpendicular distance from yellow to yellow, from triangle to triangle, from base to base, then it just needs to be perpendicular, and that would be one of its lateral edges. Could they have a dotted line that goes from the center of the triangle to the center of the other triangle? They could, but usually, they're just going to, if it's a right prism, they'll just use one of the lateral edges to indicate the height of the prism. All right. So there is one of three heights right there, or one of the not three unique ones, but they could have used any one of the three lateral edges to indicate the height. All right. Why do we call it an altitude? We want to kind of separate the word altitude and height. Now, we can use the words interchangeably, but altitude is usually used when we talk about three-dimensional objects. Height is usually for two dimensions. But if you want to use height for altitude or altitude for height, it's okay. So what happens if you don't have a right prism? Well, you would get a prism where the sides would be parallelograms and not rectangles. Notice on this one right here, the lateral edges are in fact still parallel, but they don't form 90-degree angles. We give a fancy name for this one, and this is called an oblique prism. So this chapter primarily deals with right prisms. The formulas that we get will be for the right prisms. Okay. Oh, I'm sorry, I didn't click the button there. Oblique prisms. Prisms whose lateral faces are not rectangles, but they are going to be parallelograms. All right, looks like we're almost ready. Oh, and the altitude would be measured, remember, perpendicular from base to base. Sometimes that red dotted line there will be at the center. Other times it will be set off to the side there. In this case, that they did it that way. All right. Okay, so remember, we're going to be basically doing two things for every single section. I'm going to give you the shape, and you're going to be calculating the surface area, and you're going to be calculating the volume of the shape. So let's see, what we got here? We got two parallel hexagons and the sides are rectangles. So we have a right hexagonal prism right here. So the surface area would just be the outside of the shape, and I've kind of exploded it there for you. You can notice that the sides are made up of rectangles and the bases are made up of two hexagons. So we're going to break this up into two. To calculate the surface area, we're going to break this up into two main parts. Now, here's where maybe you kind of get lost a little bit with the vocabulary. You might want to watch this twice. So here we go. So let's see. The base area of the prism would be what? The two congruent parts that are parallel to each other. Those would be the two hexagons. So those would be, I'm only pointing to one of them, but remember you got two of them. We are going to abbreviate base area with a capital letter B. Little b means base, capital B means base area. Now, since it's a prism, you're going to have two of these. So what are the other parts to the prism? Well, we've got the sides. Now, the sides are rectangles. So if we calculate the area of those rectangles, that would be called the lateral area of a prism. And it's got a fancy abbreviation, LA. So that would be that part.
This one for the other parts of the prism. Well, we got the sides. Sides are.
Well, thank you, Siri. I don't know why you actually are talking to me. All right. Sometimes my phone goes off and I didn't even say that word and just starts talking. Okay. Where are we at? Okay, so we did base area, we did lateral area. If you put those two concepts together, those two together would be the surface area. We call the surface area of a prism those two things added together, the base area plus the lateral area. We also give it a fancy schmancy name. We call it the total area. So the total area of a surface of a prism, abbreviated TA, would be made up of the lateral area plus the base area. So we got it. We're going to get to our first formula. So TA for total area of any prism, it could be triangular, rectangular, in this case hexagonal, would be the lateral area plus, well, why is there two there next to the B? Because remember, 1B would be one of the bases. Since there will always be two bases, it's going to be the lateral area plus two of the bases. So that's the formula there for total area of a prism. Now, the fun doesn't stop there because we can actually write this a little bit better. Well, that's a pretty good formula right there. Lateral area, well, that's the part we're going to make a little bit better, okay? So total area is lateral area plus two base areas. And this is going to be a theorem without a proof, sort of. I'm going to prove it, but it's just not going to be a formal proof. So let's just concentrate on the lateral area of just a right prism. This would not be true for an oblique prism, but for a right prism, the sides are all rectangles. So if I pulled those rectangles off of the prism and laid them flat like that, it would make a even larger rectangle. And we know the formula for a larger rectangle. It's base times height. So let's figure out where that would be on this picture. If you see how I stacked those three rectangles right there, so that red line would be the base of the larger rectangle that I just made, and that would be the perimeter of the base. You just think about those folding back into the prism, and that red portion, the red that I just lined right here, that would be the perimeter of the yellow. So that's the perimeter of one of the bases. And since the area of a rectangle is base times height, now that would be that portion that I'm showing there in red right now. And that would be, well, that would be the height of the prism itself. In other words, that would be the altitude. So yes, LA stands for lateral area of the prism, but the lateral area of the prism ends up being just a rectangle, and that rectangle will be the perimeter of the base times the altitude. So we get and we'll write it down here in a second, so we get an even better formula for lateral area. If you just leave LA as LA, then you're going to have to think about it. But now all we need to know is the perimeter of the base, one of the bases, times the height or the altitude of the prism. Now I'm choosing height because we're thinking of lateral area as a large rectangle and the formula is base times height, but altitude and height we can use interchangeably. So this is theorem 12.1, and it's the actual formula we're going to use for surface area. So the surface area or the lateral area of a right prism equals the perimeter of a base times the height of the prism. In other words, pH. That one's pretty straightforward. P stands for perimeter, H stands for the altitude of the prism itself. And as long as you can wrap your head around altitude and height, you'll be okay. Now remember, that's just the lateral area. That's not total area. So the first shape and first formula that we need to write down, this will not be a theorem, I'm just going to give this to you, is the surface area of a right prism. So the surface area, and here you go. This is all put together now. The surface area of a right prism, in other words, the total area, is going to be equal to the lateral area. We said that's pH from the previous theorem plus 2 of the bases. Why 2? Because it's got a top and bottom, or it's got 2 congruent parts to it. And that's the formula you're going to use tonight to do your homework for the right prisms. They won't give you an oblique prism. So I need to find the perimeter of the base, one of the yellow parts. I need to find the height of the prism, that's the H, and I need to calculate the area of one of the bases and then multiply by 2. Now, how come I can't change that capital letter B into something better? Well, because the prism itself could be any shape. It could be a triangular prism like this. It could be rectangular. It could be hexagonal. It could be octagonal. So that part will change depending upon what kind of prism you get. All right, as always, doing a okay, perimeter of the base, altitude, base area, right? As always, doing an example here will be a bit easier. Now, we're going to use the word total area and surface area interchangeably. The book uses total area. So total area equals the surface area. And remember, total area is the lateral area plus the base areas. All right. What kind of prism is that? So that is a... Well, let's see, the 2 congruent parts are going to be the trapezoids, so that's a trapezoidal prism. So it says calculate the total area of the right prism. So it's telling me it's right. We're going to calculate its total area. In other words, its surface area. So before you panic, right, you identify the shape, you write the formula. So I need the perimeter of the base. I'll try to highlight this for you. So let's see, the perimeter of the base, I'll do it in blue here. Well, the perimeter of the base would be the perimeter all the way around. I'm just choosing the top. Why? Because the top is labeled. So the perimeter all around the base here. So let's see if we can calculate that. Well, the perimeter would be, let's see, this side is 12, this side is 5, this side is 6, and this side is also, hey, look, it's an isosceles trapezoid. All right, so I just need to add 12 plus 5 plus 5 plus 6. 12 plus 10 is 22, plus another 6 is 28. So I'm getting the perimeter is 28. I need the height of the prism. This is where you're going to have a problem. So remember that first H right there, this H that's right here is not the height of the trapezoid. That's 4. It's the height of the prism, and the height of the prism is 10. That's the distance between the two bases. Okay, and remember the bases are the two parallel polygons. So this is where this 28 times 10 comes from. Okay, that's easy. Now we got to do 2 of the base areas. We don't have to, I'm going to erase everything here. We don't have to do 1 and then do a second one because they're both congruent to each other. So we just need to do 1 of the base areas. So obviously I'm going to do the top one because that's the one that has numbers on them. Well, it's a trapezoid, and we know the formula for area of a trapezoid is the height times the quantity of the two bases added together, and then divided by 2. I'm just going to plug in numbers. Of the trapezoid itself, check it out, one of the bases is 6, one of the bases is 12. The height, that's the distance perpendicularly measured between the two bases, is 4. So those are the values I'm going to throw into my trapezoid formula. 6 plus 12 times 4, that's the height, divided by 2. Okay, 6 plus 12 is 18. Half of 18 is 9, and 9 times 4 is 36. So my area of one of the bases is 36, but look at the formula. The formula doesn't say 1b, it says 2b. So I need to do 2 times 36, in other words, 72. 28 times 10 is 280, so it's 280 plus 72, which is 352. And then after all that work, you can't forget that we're doing surface area or total area, and area is measured in square units, so square centimeters here. That, my friend, is a lot of work just for calculating surface area. All right, we're not done with the fun yet. Let's calculate volume of a prism. So volume, remember, is the amount of stuff inside a three-dimensional object. It's expressed in cubic units. And I mean, I've made this point when we did area. I mean, we're literally talking about each one of these tiny cubes right here is 1 by 1 by its depth is 1. So maybe I should have done 1 by 1 by what's the dimension? I forgot. Oh, by 1. Sorry. Okay, so 1 by 1 by 1. In other words, it's 1 cube, and each one of those cubes has its dimensions of 1 by 1 by 1. And so if we counted all the cubes there, that's how many cubes make up that space, and that's why it's called measured in cubic units. All right. So back to our problem at hand, we need to calculate the volume of any shape. Another way of thinking about this, instead of thinking about how many cubes there are, that's ultimately what you're doing, is thinking about this, I don't know, think about this as pizza slices, right? You have one slice of pizza that's cut very, 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 very thin, and then you stack another pizza slice. And then you stack another piece of slice. Why am I going from top to bottom? I should be going from bottom to top, but you get the idea. Stack, stack, and I'm just stacking pizza slices. Well, how many did you stack? Well, how many did you stack would be equal to the, well, how tall is this prism? And that would be its altitude or its height. So basically the formula, therefore, would be the area of one of those pizza slices times how many pizza slices there are, and that's the distance between top and bottom. So this is the general formula for all prisms. And that formula is V for volume is equal to capital B. Now remember, we said capital B is the base area. So capital B is the area of one of the bases times the height or the altitude of the prism itself. So it turns out that volume is way easier to calculate than surface area or total area. Total area, it's a pretty darn complicated formula. It's pH plus 2b, whereas this is just capital B times h. Okay? The issue is why this generally appears easy is that, well, it's a capital B, it's not a little b. So capital B is, well, technically it is one number, but it's calculated by calculating the area of one of the bases. So in the case of our trapezoid, then we got a little bit of work to do. In the case of our triangular prism right here, we got to calculate the area of one of the triangles and then multiply it by the altitude. So back to our ugly problem right here. Sorry, trapezoidal prism. We're going to calculate its volume. Well, it's just this formula. We already know the height, how far is it from trapezoid to trapezoid? Well, that was the 10 value right here. Should do that in blue. That is the 10 value right here. So all I need to do now is calculate one of the base areas. And we've already done that before on when we did surface area, but if you forgot, well, then we got to plug it back, the values back into our trapezoid formula. Remember the two bases were 6 and 12, and the height was 4. 6 plus 12 is 18. 18 divided by 2 is 9. 9 times 4 is 36. So one of the base areas is 36, and that's all I need for this form is one of them, and I need to multiply it by the height. And as I stated before, typically the volume formula is way easier to use than the surface area or total area formula. Just remember that the units are always measured in cubic units. Okay. The more challenging ones, well, how do they make any of this challenging? They just take off of the, one of the necessary values that we need, and they give us the surface area, or they give us the volume, and have you solve for that. So it says calculate the total area of this right prism, and notice, well, it's a triangular prism. The top and the bottom that are congruent are triangles, and the sides are rectangles. And they give us the volume. Well, volume has nothing to do with surface area. So somehow I'm going to get the required values that I need for total area out of the volume. So if you're asked to calculate the total area, that's the formula that you're going to start with. So total area of any prism, as long as it's right, is pH plus 2b. So let's see, what do I need when I do that? Well, if I plug in what I have, the perimeter, where did I get the perimeter? I go to one of the bases, and I simply do the perimeter. 7 plus 6.5 plus 10.5. 10.5 and 6.5 are 17, and 17 plus 7 is 24. That's where the 24 came from. Okay. Well, let's move it on. Can we get any other information? Well, I can do the base area, right? The base area, and I need two of them, is a triangle. And if I look at the triangle, let's see, the base is, well, I'm looking for a dotted line, red dotted line. There's one right there next to 10.5. So the base is 10.5 and the height is 4. So 10.5 times 4 is what? 4 times 5, 20, carry my 2. So 42, and then half of 42 is 21. So the area of one of those triangles is 21. And now maybe I can plug those values in, right? Well, if I plug that 21 in for B, I've got mine. I probably should have done that immediately. So I can plug that 21 in for the B, and the only thing I'm missing now is the height. Remember, the height is not the height of the triangle. The height is this height right here, the distance between the two triangles. So now I'm going to switch back to my volume formula because that has the same H. And since I just calculated that the area of one of the bases is 21, that's the B I need for that formula. Okay. All right, so let's see how this works. Let's see, we're told 315 is equal to the volume, and that's equal to capital B times H, and I just found out that capital B was 21, so now I can solve for H. So I'm going to divide 315 by 21 with my handy-dandy calculator, and I get the height is 15, and that's the value that I need to throw into. I'm going to erase everything now. That's the value that I need, this 15 gets plugged into this H, and 21 gets plugged into this B, and now I have everything. Okay, so now it's just a calculator drill. You can do that one pretty simple. 24 times 15, add that 2 plus 21, and you're done. And remember, we're doing total area, so it will be measured in square units. In this case, no numbers or no values are listed for my units, so I just put square units. That seems like a lot of work, and it is a lot of work. All right, so wow, indeed. All right, homework for 1 through 12 is going to be a table. They're just going to give you all that stuff, and remember, they're just going to, the first couple ones are going to be pretty straightforward, and then they're going to erase some things. Do I have a table here? I don't, just show you an example of here, but it is pretty straightforward, table 1 through 12. If you have any problems, as always, just send me a quick email. I'd be more than happy to help you out. Okay, So good luck with your homework. I might want to watch this video again as you're doing your homework just so that's fresh in your mind. Okay, that'll do it, and I will see you next class.